Good morning. Hi. My name is Hong-Lak Lee. I'm going to be a session chair for the morning. So it's my great pleasure to introduce Koray Kavukcuoglu, who is going to give an invited talk. Koray is a director of research in DeepMind, and he's one of the star researchers in our community. He has contributed to many highly influential projects in DeepMind, such as spatial transformer networks, autoregressive generative models, such as pixel recurrent networks and wavenets, and deep reinforcement learning for playing Atari games and AlphaGo. Today he will talk about from generative models to generative agents. So let's welcome Koray.
Thank you very much, Hong-Lak, for the very nice introduction, and thanks everyone for being here. It's an absolute pleasure. So as Hong-Lak mentioned, I'm going to try to talk about unsupervised learning in general, starting from the generative models, maybe a classical view, and I try to give another view that I think is quite interesting that we have been working on recently. When I think about what are the important things for us to do as a community, I think everyone here sort of agrees that in the end what is important is to be doing unsupervised learning. We sort of realize that supervised learning has all sorts of successes, but in the end unsupervised learning is kind of like the next frontier. And when I think about unsupervised learning, there are sort of like different explanations that come to my mind, and when talking to people, I think we all have sort of different opinions on this. One of the things that I think is a common explanation is we have an unsupervised learning algorithm, we run it on our data, what we expect is the algorithm to understand our data and to explain our data or our environment, right? And what we expect from this is that the algorithm is going to learn the intrinsic properties of our data, of our environment, and then it's going to be able to explain that through those properties. But most of the time, what happens is, because of the kinds of models that we use, we resort to, at the end, looking at samples. And when we look at the samples, we try to see that did our model really understand the environment, and if it understood the environment, then the samples should be meaningful. Of course, we look at all sorts of objective measures that we use during training, like inception scores, log likelihoods, and such. But in the end, we always resort to samples in terms of like understanding if our model really can explain what's going on in the environment. The other kind of general explanation that we all use is like the goal of unsupervised learning is to learn rich representations, right? It's already embedded in the name of this conference. The main goal of deep learning, unsupervised learning, is learning those representations. But then when we think about those representations, again, this explanation doesn't give us an objective measure. What we think about is why those, like how are we going to think about those representations in terms of being rich and useful? And to me, the most important bit is if we have good and rich representations, then they are useful for generalization, for transfer, right? And we need to sort of, if we have a good unsupervised learning model and it can give us good representations, then we can get generalization. So what I'm going to do is today also tie it together with something else that is really, I think, for me, at least very important, as Hong-Lak mentioned, a big chunk of work that we have been doing at DeepMind, that I've been doing, is about agents and reinforcement learning. And in this talk, I'm going to sort of take a look at unsupervised learning from classical sense of like learning a generative model and also learning an agent that can do unsupervised learning. So I'm going to start from the wavenet model. Hopefully, as many of you know, it's a generative model of audio. It's a pure deep learning model, end-to-end. It does, you can model any audio signal like speech and music, and then you can get really realistic samples out of that. And the next thing I'm going to do is I'm going to explain this other sort of new approach that I find really interesting to unsupervised learning, that is based on deep reinforcement learning, learning an agent that does unsupervised learning. So this model called Spiral is based on a new agent architecture that we have been working on, that we have published recently, called Impala. It's a very large, highly scalable, efficient off-policy learning agent architecture that we use in Spiral to do unsupervised learning. And the interesting bit about the spiral work is it does generalization through using some sort of tool space, tools that we as people have created, so that we can actually solve not one specific problem, we can solve many different problems using these tools. And using the interface of a tool and having an agent, you can actually now learn a generative model of your environment. All right, so without more delay, the first thing that I'm going to try to introduce is quickly the WaveNet model. WaveNet is a generative model of audio. As I said, it samples the raw audio signal. It doesn't use any sort of interface to model the audio signal. Audio in general is very, very high dimensional. So the standard audio signal that we started when we were at the beginning was 16,000 samples per second. Like if you compare that to our usual language modeling and machine translation kind of tasks, it is several orders of magnitude more data. So the kinds of dependencies that one needs to model to be able to model good audio signals is very long. So this model, what it does is it samples, it models one sample at a time, and it uses a softmax distribution to model each sample dependent on all the previous samples of the signal. When you look at it more closely, though, it is an architecture that has quite a bit of resemblance to the pixel CNN model. Maybe some of you also are familiar with that. In the end, it is a stack of multiple convolutional layers. To be a little bit more specific, it has these residual blocks. You use multiples of those residual blocks, and in each residual block there are these dilated convolutional layers that go on top of each other, and through those dilated convolutional layers that are causal convolutions, we can model very long dependencies. So through that, we can get the modeling dependency in time. Now, one of the biggest design considerations about WaveNet is it is designed to be very, very efficient during training. Because during training, what you can do is, because all the targets are known, when you generate the signal, you generate the whole signal at once, just run it like a convolutional net, you get your signal, then because you have the targets, you get your error signal from that, propagate back. So training is very efficient. But of course, when it comes to sampling time, in the end, this is an autoregressive model. And through those causal convolutions, you need to run through them one sample at a time. So if you are sampling at, say, 24 kilohertz, 24,000 samples per second, you need to generate one sample at a time, just like you see in this animation. And of course, this is painful. This is painful, but in the end, it works quite well. And we can generate very, very high quality audio with this. So what I want to do is I want to make you listen to the unconditional samples from this model. So when we model the speech signal, and without any conditioning on text or anything, just take the audio signal and model that with WaveNet, and then when you sample, this is the kind of
Okay, panels, the extrude report list headlinings and insist subjects with us, Carol Baldwin's went wars.
So as you can see, or hear, hopefully, the quality is very high, and this is modeling really the raw audio signal, and this is completely unconditional. So what you hear is sometimes you even hear short words like "okay," "from," and then if you try to listen, all the tonation and everything sounds quite natural. And sometimes it feels like you are listening to someone speaking in a language that you don't know. So the main characteristics of the signal is all captured there. So in terms of dependencies, we are looking into something like several thousand samples of dependencies are actually properly and correctly modeled there. And then, of course, And then, of course, what you can do is you can augment this model by conditioning on a text signal that is associated with the signal that you want to generate. And by conditioning on the text signal, now you have a generative model, a conditional generative model that actually solves a real-world problem just by itself, end-to-end deep learning. Right? So you have the text, you create the linguistic embeddings from that. Using those linguistic embeddings, you can generate the signal. And then it starts talking, right? So it's a solution to the whole text-to-speech synthesis problem that, as we know, is very, very common, used in in real world. Sorry. All right. So when we did this, the WaveNet model, and this was around like almost 2 years ago now, we looked at the quality when we used it as a TTS model. And in green, what you see is the quality of the human speech, like obtained through this mean opinion scores. And in blue, you see the WaveNet, and the other colors are the other models that were the best models around at the time. And you can see that WaveNet closed the gap between the human quality speech and other models by a big margin. So at the time, this really got us excited because now we actually had a model, a deep learning model that comes with all the flexibilities and advantages of doing deep learning, and at the same time, it's modeling raw audio, and it is very, very high quality. I could play text-to-speech samples that is generated by this model, but actually what you can do is what I'm going to go into next. If you are using Google Assistant right now, you are already hearing WaveNet there because this is already in production. So anyone who's using Google Assistant and like querying Wikipedia and things like that, the speech that is generated there is actually coming from the WaveNet model. And what I want to do is I want to explain how we did that. And that brings me to our next project that we did in the WaveNet in the WaveNet domain. This is the parallel WaveNet project. So of course, when you have a research project, and at some point you realize that okay, it actually lends itself into the solution of a real world problem, and you want to put it into production in a very challenging environment, then of course it requires much more than our little research group. So this was a big collaboration between the DeepMind research, applied, and the Google speech teams actually. So in this slide, what I show is the basic ingredients of how we turn a WaveNet architecture into a feed-forward and parallel architecture. Because what we realized pretty soon, when we tried to attempt putting a system like this into production, was actually speed, of course, is very important. Quality is very, very important. But the importance of speed is, it is not enough to actually run something in real time. The kind of constraints that we tried to solve was like orders of magnitude faster than real time, even actually being able to run in constant time. So when the constraint becomes being able to run in constant time, the only thing you can do is create a feed-forward network and then parallelize the signal generation, right? So that is what we did. So in this slide, at the top, what you see is the usual WaveNet model. We call it the teacher now in this setting. This WaveNet model is pre-trained, and it is fixed. And it is used as a scoring function. At the bottom, what you see is the generator that we call the student. And this student model is, again, an architecture that is very close to WaveNet, but it is run as a feed-forward convolutional network. And the way it is run is, and it is trained, is actually it has two components. One component is coming from WaveNet. We know that it is very efficient in training, as I said, but slow in sampling. The other thing is based on the inverse autoregressive flow work that was done by Dirk Kingma and his colleagues at OpenAI last year. And this structure gives us the capability to actually get an input noise signal in and slowly transform that noise signal into a proper distribution that is going to be the speech signal, right? So the way we train this is random noise goes in together with the linguistic features. Through layers and layers of these flows, the signal gets, that random noise gets transformed into speech signal. That speech signal goes into WaveNet. WaveNet is like already the best kind of scoring function that we can use because it's a density model. And WaveNet scores that, and that score, from that, we get the gradients back into the generator, and then we update the generator. We call this process the probability density distribution. But of course, when you're trying to do real-world things, and things are very challenging, like speech signals, that is by itself not enough. So I have highlighted two components here. One of them, as I said, is the WaveNet scoring function. The other thing that we use is a power loss, because what happens is when we train the model in this manner, the signal tends to be very low energy, sort of like whispering. Someone speaks, but they are like whispering. So during training, we sort of added this extra loss that tries to conserve the energy of the generated speech signal. And with these two, the wavenet scoring and the power loss, we were already getting very high quality speech signal. But of course, like the constraints are very, very tough. And what we did was we trained another wavenet model. So we sort of used wavenet everywhere, right? Like we are generating through a wavenet through convolution. We are using wavenet as a scoring function. We again trained another wavenet model. This time we used it as a speech recognition system. And that is the perceptual loss that you see there. So we trained the wavenet again as a speech recognition system. What we do is during training, of course, you have the text and the corresponding speech signal. We generate the corresponding speech through our generator. We get the text, give that to speech recognition system. The speech recognition system, of course, now needs to decode the generated signal into that text, right? And we get the error from there, propagate back into our generator. So that's another sort of quality improvement that we get by using speech recognition as a perceptual loss in our generation system. And the last thing that we did was using a contrastive term that basically uses, okay, you generate a signal conditioned on some text. You can create a contrastive loss where saying that the signal that is generated with the corresponding text is should be different than the same signal if it was conditioned on a separate text, right? And there's a contrastive loss term. So more specifically, what we have is in the end we end up with these 4 terms. At the top, we see that the original sort of using wavenet as a scoring function, the probability density distillation idea. Then we have the power loss that uses Fourier transforms with an L2 to conserve the energy, and the contrastive term, and finally the perceptual loss that does the speech recognition. And when we all these, then of course what we did was we looked at the quality. Now what I'm showing here is the quality with respect to the, again, the best non-wavenet model. So this is sort of like a year after the original research, pretty much exactly a year. And so during that time, of course, the best speech synthesis models also improved, but wavenet was still better than anything else, and it was matching the quality of, so the new wavenet, the parallel wavenet, is exactly matching the quality of the original wavenet too. And what I'm showing here is 3 different US English voices and also Japanese. And this is the kind of thing that we always want from deep learning, right? The ability to generalize to new data sets, to new domains. So we have developed all this model on practically one single US English voice. And it was just a matter of collecting or getting another data set from another either speaker or another language, like some speaker speaking Japanese. You just get that, run it, and there you go. You have a speech synthesis. You have a production quality speech synthesis system just by doing that. This is the kind of thing that we really like from DeepMind, right? And if you are thinking about from deep learning, and if you are thinking about unsupervised learning, I think this is a very good demonstration of that. So before switching to the next one, I also want to mention that we have also done some further work on this called WaveRNN that is recently published, and I encourage you to look into that one too. That's a very interesting piece of work also for generating speech at very, very high speed. The next thing I want to talk about is the Impala architecture, the new agent architecture that I said, because as I said, so now WaveNet is a sort of, in a classical sense of unsupervised model that actually can solve a real-world problem. Now, the next thing I want to sort of start talking about is this new, different way of doing unsupervised learning. But for that, another exciting bit is to be able to do deep reinforcement learning at scale. Sorry. All right. So I want to sort of motivate why do we want to actually push our deep reinforcement learning models further and further. Because most of the time, what we do, because this is a new area, is we take sort of like very simple tasks in some simple environments, and what we try to do is we try to train an agent that solves a single task in that environment. Well, what we want to do is we want to go further than that, right? Like, again, going back to the point of generalization and being able to solve multiple tasks. We have created a new task set. This is an open source task set that we have an open source environment called DMLab, and as part of that, we have created this new task set, DMLab 30. It is 30 environments that are sort of covering tasks around language, memory, navigation, and those kinds of things. And the goal is not to solve each one of them individually. The goal is to have one single agent, one single network that is solving all those tasks all at the same time. There's nothing custom in that agent that is specific to any single one of these environments. When you look at those environments, I'm showing some of those here. The agency has a first-person view, so it is in like a maze-like environment, and the agent has a first-person view camera input, and it can navigate around, go forward, backwards, and rotate around, look up, down, jump, and those kinds of things. And it is solving all different kinds of tasks that are catered to test different kinds of abilities. But the goal is, as I said again, to solve all of them at the same time. One thing that becomes really, really important in this case is, of course, the stability of our algorithms, because now we are not solving one single task, we are solving 30 of them, and we want really stable models because we don't have the chance to tune hyperparameters one single task anymore. And of course, what becomes really important is task interference, right? Hopefully what we expect, again, by using deep learning is this is like a multitask setting, and in this multitask setting, we hope to see positive transfer rather than task interference, and we hope to demonstrate this in this challenging reinforcement learning domain too. Okay. I sort of realized that I needed to put a slide about why deep reinforcement learning, because a little bit to my surprise, there was actually not much reinforcement learning in this conference this year. And I wanted to sort of a little bit touch on why I think is important for the deep learning community, for this community to actually do deep reinforcement learning. Because to me, it is at the core of, if one of the goals that we work for here is AI, then it is at the core for that, right? Reinforcement learning is a very general framework for doing sequential decision-making, for learning sequential decision-making tasks. And deep learning, on the other hand, of course, is the best model that we have, the best set of algorithms we have to learn representations. And combinations of those, combinations of these two different models is the most sort of like is the best answer so far we have in terms of learning very good state representations of very challenging tasks that are not just for like solving toy domains, but actually to solve challenging real-world problems. Of course, there are many things that are open problems there. Like some of them that are sort of interesting, at least for me, is the idea of separating the computational power of a model from the number of weights or the number of layers it has, or basically, again, going back to unsupervised learning to transfer, right? So we do this deep reinforcement learning models with the idea to actually generalize, to transfer. Okay, so the Impala agent is based on on another work that we have done a couple of years ago called the asynchronous advantage actor critic, the A3C model. In the end, it's a pulse gradient method. What you have is like that. I tried to sort of cartoonishly explain there in the figure. At every time step, the agent sees the environment, and at that time step, the agent outputs a policy distribution and also the value function. The value function is the agent's expectation of the total amount of reward that it's going to get until the end of the episode, being in that state, right? And the policy is the distribution over the actions that the agent has. And at every time step, the agent looks at the environment and updates its policy so that it can actually act in the environment, and it updates its value function. And the way you train this is with the policy gradient. Intuitively, this is actually very simple. What you do is the gradient of the policy is scaled by the difference between the total reward that the agent actually gets in the environment minus the baseline. And the baseline is the value function, right? So what it means is if the agent ends up doing better than what the value function, what its assumption was, then it's a good thing. You have a positive gradient, you are going to reinforce your understanding of the environment. If the agent does worse than what it got, so the value was higher than the total reward that you got, then you have a negative gradient, you need to shuffle things around. And the way you learn the value function is by the usual n-step TD error. Now, the A3C algorithm, so this was the actor critic part. The asynchronous part, the A3C algorithm, is composed of multiple actors, and each actor independently operates in the environment and collects observations, acts in the environment, computes the policy gradients, and computes the gradients with respect to the parameters of its network. Then what it does is it sends those gradients back into the parameter server. Then the parameter server collects all these gradients from all different actors, combines them together, and then shares those parameters with all the actors around. Now, what happens in this case is as you increase the number of actors, this is the usual asynchronous stochastic gradient descent setup. As the number of actors increases, the staleness of the gradients becomes a problem. So what happens is in the end is distribution experience collection is actually something very, very advantageous. It's very good. And, but what happens is communicating gradients might become a bottleneck as you try to really scale things up. So for that, what we tried was a different architecture. The idea of a centralized server is actually quite useful, but rather than using it to just do accumulate the parameter updates, the idea of that learner is to make that centralized component into a learner. So the whole learning algorithm is contained in that. What the actors does is only act in the environment, not compute the gradients or anything, send the observations back into learners, to the learner, and the learner sends the parameters back. And in this way, what you are doing is you are completely decoupling what happens about your experience collection in your environments from your learning algorithm. And in this way, you're actually gaining a lot of robustness into noise in your environments. Sometimes rendering times vary. Some environments are slow, some environments are fast. All that is completely decoupled from your learning algorithm. But of course, what you need is a good learning algorithm to be able to deal with that kind of variation. So in the end, with Impala, what we have is we have a very efficient decoupled backward pass, if you will. So actors generate trajectories, as I said, but then that decoupling creates this off-policiness, right? The policy in the actors, the behavior policy, if you will, is separate from the policy in the learner, which is the target policy. So what we need is an off-policy learning. Of course, there are many off-policy learning algorithms, but we really wanted to have a policy gradient method. And for that, we developed this new method called vtrace, and it's an off-policy advantage critic algorithm. The advantage of vtrace is it is using these truncated importance sampling ratios to actually come up with an estimate for the value. So because there's this imbalance between the learners and the actors, you need to balance those. You need to balance that difference. The good thing about this is it's an algorithm where it's a smooth transition between the on-policy case and the off-policy case. When the actors and the learner are completely in sync, so you are in the on-policy case, the algorithm actually boils down to the usual A3C update with the n-step Spellman equation. If they become more separate, then the correction of the algorithm kicks in, and then you have the corrected estimate. The algorithm has two main components, those truncation factors, to control two different aspects of learning. One of them is the row, which controls which value function the algorithm is going to converge towards. The value function that corresponds to the behavior policy, or the value function that corresponds to the target policy in the learner. And the other one controls the speed of convergence, the C factor. By controlling the truncation depth, it can increase or decrease the variance in learning, and thus it can have an effect on the speed of convergence. Now, when we tested this, of course, the goal is to test on all environments at once, but what we wanted to do was, first you look at the single task results. So we look at 5 different environments, and we see that in these environments, the Impala algorithm always very stably performs at the top. So the comparisons here are the Impala algorithm, the batch A3C method, and the batch A2C method, and different versions of A3C algorithms. And you can see that Impala and batch A2C are always performing at the top. Impala seems to be doing fine. They're like the dark blue curve. And this gives us the sort of feeling that, okay, we have a nice algorithm. Now, of course, the other thing that is very important and that is discussed a lot is the stability of these algorithms, right? I actually really like these plots. Since doing the A3C work, actually, we keep looking at these plots, and we always put them in the papers. The plot here is on the x-axis. We have the hyperparameter combinations. When you, of course, train any model, what we do, all of us, is we do some sort of hyperparameter sweep. And here what we are doing is we are looking at the final score that we achieve with every single hyperparameter setting that we get, and you sort it. And in this kind of plot, what you have is the curves, the algorithms that are at the top and that are most flat are the most better performing and most stable algorithms, right? And what we see here is Impala is always, of course, it's achieving better results, but it's not achieving those results because there's one sort of lucky hyperparameter setting is consistently at the top. And you can see that it's not, of course, completely flat because in the end we are sort of searching over 3 orders of magnitude in parameter settings. But we can see that the algorithm is actually quite stable. Now, when we look at our main goal, here what we are looking at is on the x-axis we have the walk log time. And on the y-axis we have the sort of the normalized score. And the red line that you see there is the A3C. And you can see that Impala not only achieves much better scores, it achieves them much, much, much faster. The other thing is comparing the green and the orange lines there that is the comparison between training Impala in an expert setting versus a multitask setting. And we see that it achieves better scores slightly faster, which again gives us the idea that we are actually seeing positive transfer. It's a like-to-like setting. All the details of the network and the agent are the same. In one case, you have one network per task. In another case, you train the same network on all the tasks. And what you achieve is a better result because of the positive transfer between those tasks. And what happens is, if you give Impala more resources, you end up with this almost vertical takeoff from there, right? And what you have is you can actually solve this challenging 30-task domain in under 24 hours, given the resources. And that is the kind of algorithmic sort of power that we want to be able to train these very highly scalable agents. Now, why do we want to do that? That is the point that I want to come next. And the final part, this is the new spiral algorithm that I want to talk about. Now, just quickly going back to the original ideas that I talked about, unsupervised learning is also about explaining environments and generating samples, but maybe generating samples by explaining environments. And we talk about the fact that when we have these deep learning models like WaveNet, we can generate amazing samples. But at the same time, maybe there's a different way we can do these things, less implicit, in the sense that when we generate these samples, they come with some explanation. And that explanation can go through using some tools. In this particular case, what we are going to do is we are going to use a painting tool. And we are going to learn to control this painting tool. It's a real drawing program. And we are going to basically generate a program that the painting tool will use to generate the image. And the main idea that I want to convey is by using tools, by learning how to use tools that are already available, that we have, actually we can start thinking about different kinds of generalization that I'll try to demonstrate. So in real world, we have a lot of examples of programs and their executions and the results of those programs. They can be arithmetic programs, drawing programs, or even architectural blueprints, right? And what we do is, because we know we have an information on that generation process, when we see the results, we can go and try to infer what was the program, what was the blueprint that generated that particular input. So we can do this, and the goal is to be able to do this with our agents too. Specifically, we are going to use this environment called LibMyPaint. It is actually a professional-grade open-source drawing library, and it's used worldwide by many artists. What we are doing is we are using a limited interface, basically learning to draw brush strokes. We are going to have an agent that does that. The agent in the end, called Spiral, has 3 main components. First of all, is the agent that generates the brush strokes. Sort of, I like to see that as writing the program. The second one is the environment, the LibMyPaint. So the brush strokes come in, environment turns those into brush strokes in the canvas, and that canvas goes into a discriminator. And the discriminator is trained like a GAN, and that discriminator looks at the generated image and says, does this look like a real drawing? And then gives a score. And that score, as opposed to the usual GAN training, rather than propagating the gradient packs, We get that score, and we train our agent with that score as a reward. So when you think about this, all these three components coming together, you have an unsupervised learning model similar to the GANs, but rather than generating in the pixel space, we generate in this program space, and the training is done through the reward that the agent itself also learns. So we are sort of trusting another neural net, just like in GAN setup, to actually guide the learning, but not through its gradients, just through its score function. So in my opinion, it makes it, in certain cases, it makes it very, very sort of capable of using a different kinds of tools. So as I said, this agent, the reinforcement learning part of the agent is completely the same as the Impala. So now that we have an agent that can actually solve really challenging reinforcement learning setups, we take it and put it into this environment, augment it with the ability to learn a discriminative function to actually have the reward. To emphasize again, the important thing here is, yes, we have an agent, but there is no environment that actually says that, okay, this is the reward that the agent should get. The reward generation is also inside the agent, thanks to, again, all the unsupervised learning models that is actually being studied here. So we specifically use a GAN setup there. So can we generate? The first thing, of course, we try is when you are doing unsupervised learning from scratch, again, you go back to MNIST, right? You start from MNIST. And initially, of course, it's generating very scratchpad-like things, but then through training, it becomes better and better and better. Here in the middle, you see that now the agent learned to, these are completely unconditional samples, again, the ones that you see in the middle. It learned to create these strokes that generates these digits, right? To emphasize, this agent has never seen strokes that are coming from real people, how we draw digits. It learned to experiment with these strokes, and it sort of built its own policy to create these strokes that would generate these images. Of course, you can train the whole setup as a conditional generation process to recreate a given image too. I think the main thing about this is it's learning an unsupervised way to draw the strokes. I see it as the environment, the LibMyPaint environment sort of gives us a grounded bottleneck to actually create a meaningful representation space. Of course, the next thing we tried was omniglot, and again, you see the same things. It can generate unconditional, meaningful omniglot looking like samples, or it can recreate omniglot samples. But then, generalization, right? So here, what we tried was train the model on omniglot, and then ask it to generate MNIST digits, right? This is what you see in the middle row there. Can it draw MNIST digits? This has never seen MNIST digits before, but we all know that omniglot is more general than MNIST, and it can do it, right? Given an MNIST digit, it can actually draw that. The network itself has never seen any MNIST digits during its training. Then we tried smileys, right? They are line drawings. Okay, so it can, given a smiley, it can also draw smileys too. That is great. So can we do more? We did this, we took this cartoon drawing, and this is done by chopping it up into 64 by 64 pieces, and it's a general line drawing, right? Again, this is the same agent that is trained using omniglot. And now you can see that it can actually recreate that drawing. Certain areas are really bad, right? Like around eyes and such, they are really complicated. But in general, you can see that it is actually capable of generating those drawings. So this gives you an idea of, okay, generalization. I can sort of train on one domain and generalize to new ones. So can I push it further? The next thing that we tried was, okay, the advantage of using a tool is you have a meaningful representation space that we can hopefully transfer that representation space into a new environment. So here what we do is, again, the same agent that is trained using omniglot, we transfer that simulated environment into real world. The way we do that is we took that same program, and our friends at the robotics group at DeepMind wrote a controller to control that robotic arm, to take that program and draw it. This whole experiment happened in under a week, really, and what we ended up with was the same agent, it is not fine-tuned through all the setup or anything. The same agent generates its brush stroke programs, and then that program goes into a controller that can be realized by a real robotic arm. Right? The advantage of doing this is the reason we can do this is the environment that we used is a real environment. We didn't sort of create that environment. the latent space, if you will, is not something, some arbitrary latent space that we created, because it's a latent space that is defined by us, that is as a meaningful tool space. And the reason we create those tools is to solve many different problems anyways, right? And this is an example of that. Using that tool space gives us the ability to actually transfer with this capability. So with that, I want to conclude. I tried to give an explanation of, we think about generative models and unsupervised learning. And to me, of course, like I'm 100% sure everyone agrees that our aim is not to just look at images, right? Our aim is to do much more than that. And I tried to give two different aspects. One of them is the kind of generative models that we can do actually right now can solve real-world problems like we have seen in VUNet. And also we can think about a different kind of setup where we have agents actually training and generating interpretable programs. Right? That is an important aspect that we have seen that conversation coming up here actually through several of the talks here, that being able to generate interpretable programs is one of the bottlenecks that we face right now, because there are many critical applications that we want to solve, there are many tools that we want to utilize. And this is one sort of step towards that. That's the way how I see it. And being able to do these requires us to create these very capable reinforcement learning agents that rely on new algorithms that we need to work on. With that, thank you very much, and I want to thank all my collaborators for their help on this. Thank you very much.
We have time for maybe one or two questions. Okay, so I have one question.
Sure.
So how do you think about scaling to more general domains beyond some simple line stroke drawings? How to generate realistic scenes from this program approach.
Right. So one thing that I haven't shown here actually, yes. So creating realistic scenes is one case. One thing that I haven't talked about is actually as part of this work, it's actually in the paper. One thing that the team did. By the way, I have to mention this was work done mostly by Yaroslav Ganin, where he's actually a PhD student at Mila, and he spent his summer with us doing his internship. This was an amazing job for actually doing an internship. Very, very big congratulations to him. So one thing that we did was actually try to generate images. So we took the Celebay data set and used the same drawing program to actually draw those. And in that case, our setup is just scaling towards those. Like the same setup actually scales because it's a general drawing tool, and you can control the color, and we can do that. But it requires a little bit more sort of it was one of the last experiments that we did. But it is sort of in the works.
Right, thanks for a great talk. I had a question about the Impala results.
Right.
You had a slide where with a curve where all workers are learning versus having one centralized learner. The all workers learning actually does better than the centralized learner, and I found that not quite surprising, but it's great, and it's great to see the positive transfer between tasks. Have you tried that on other suites of tasks? Do you think it's just because it's tasks in this suite of tasks are very similar to each other?
It definitely depends on that. But the reason we created those task sets is for that reason, right? In real world, what we have is the visual structure of our world is unique. So the kind of setup that we have in DeepMind lab, that task suite is that it's a unified visual environment. You have one sort of one kind of agent with a unified action space. And now you can focus on solving different kinds of tasks. Of course, that is the kind of thing that we were testing. Given all these true, is it possible to do the multitask positive transfer that we see in supervised learning cases, that we'll be able to see that in reinforcement learning? Yeah.
Thanks.
Hello. This is exciting. I have a question about extending this to maybe more open domains. So what is the challenge? Is the challenge to be the number of actions to pick? Because the number of strokes, maybe the stroke space is smaller. So what are the challenge to extend to open domains?
What do you have in mind as open domains? Like number of actions is definitely a challenge, right? It is definitely one of the big challenges that a lot of research, as far as I know, in RL goes into that. But that is, I think, only one of the main challenges. The other challenge, of course, is the state representation. That is mainly why we sort of use deep learning, right? Because we expect that with deep learning we are going to be able to learn better representations, and that still remains as a challenge because being able to learn representations is not an architectural problem only. It is also about finding the right sort of training setup. And Spiral was an example of that, where we can get that reward function, that reward signal in an unsupervised way, right? And in many different domains, like there are many different ways we can do this, but actually finding those solutions also part of that.
Okay, so let's thank Koray again.